In the last program, you applied the formulas governing series circuits to determine the voltage, current, resistance, and power using only a schematic and mathematics. Now, in this program, you'll be introduced to parallel circuits. You'll be shown what they are and shown the relationship between voltage, current, resistance, and power when parallel resistors are connected in a circuit. In addition, you'll be introduced to both the reciprocal formula and the product divided by the sum formula, both of which are used to determine the total resistance in a parallel circuit.
A parallel circuit contains more than one path for current to flow with the same voltage source for each path. For example, here are two schematics. The top one represents a series circuit. Notice that there's only one path for current to flow. However, the bottom schematic represents a parallel circuit. Unlike the series circuit above it, the parallel circuit has more than one path for current to flow. This parallel circuit has two separate paths for current to flow. If each path is carefully traced, you should notice that each individual path is connected to the negative and positive poles of the power supply. In other words, each separate path has the same voltage source. When resistors are connected in a circuit this way, they are said to be connected in parallel. Each separate path is referred to as a branch. Each additional branch in a parallel circuit has an effect on total current. To see this effect, you'll build a parallel circuit on a breadboard.
Referring to the schematic, 3 ammeters will be connected to the circuit. One to measure total current, and one in each of the 2 branches to measure individual branch current. In addition, the resistance in the 2 branches will be rated at 1,000 ohms each. Finally, the total voltage being supplied will be 5 volts.
To begin, first make sure that the power supply is off. Next, get a notepad so that you can record your observations. Make 3 columns, one each for voltage, current, and resistance. Under the column for current, list IT for total current, IR1 for the first branch current, and IR2 for the second branch current. Under the column for resistance, list RT for total resistance, R1 for the resistance of the first branch, and R2 for the resistance of the second branch. Next, using a digital ohmmeter, verify the value of the first resistor to make sure it's within tolerance. The meter reads 1,000 ohms, which is the nominal value. Record this for R1. You can now insert the first resistor's axial leads into the breadboard. Set the first axial lead in the upper half of the breadboard above the center canal, and the second axial lead in the bottom half of the breadboard below the center canal. Use the ohmmeter again to verify that the second resistor is within tolerance. The meter reads 1,002 ohms. Record this next to R2.
Now you can insert this second resistor. Again, set the first axial lead in the upper half of the breadboard, above the center canal, and the second axial lead in the bottom half of the breadboard, below the center canal. Now connect the resistors together by connecting the 2 leads on the bottom side of the canal with a jumper wire. Then connect the negative black clip lead to the resistor on the left by connecting it to the axial lead of the resistor below the canal. Next, connect the black negative banana lead to the power supply, and connect the black negative clip lead from the branch 1 ammeter to the top lead of the first resistor. Next, connect the red positive clip lead from the total current ammeter to the red positive clip lead from the power supply, and connect the red positive banana lead into the power supply. Then, connect the red positive clip lead of the branch 1 ammeter to the black negative clip lead of the total current ammeter. Next, connect the black clip lead of the second branch ammeter to the top axial lead of the second resistor. Finally, connect the red second ammeter clip lead to the connection of the first branch ammeter and the total current ammeter. Turn on the DC power supply and adjust its output to 5 volts. On your notepad, record 5 volts next to total voltage, ET. Look at ammeter 1, which is measuring total current. It's reading 10.0 milliamps. Record this on your notepad for IT. Look at ammeter 2, which is measuring the current in your first branch. It's reading 5.0 milliamps. Record this on your notepad for IR1. Finally, look at the third ammeter, which is measuring the current in the second branch. It's reading 5.0 milliamps. Record this on your notepad for IR2. Notice that each of the branch currents is less than the total current. However, if you add each of the branch currents together, that is 5 plus 5, their sum, 10 milliamps, is equal to the total current.
Now add a third 1,000 ohm resistor to the circuit. Referring to the schematic, the third resistor will be added in parallel with the first two resistors. In addition, another ammeter will also be added to measure the current in the third branch. Turn off the power supply. On your notepad, make another chart for voltage, current, and resistance. Under the column for voltage, record 5.0 volts for total voltage. Under the column for resistance, record 1,000 ohms for R1 and 1,002 ohms for R2. Use the ohmmeter to verify that the third resistor you're adding to the circuit is within tolerance. The meter reads 1,004 ohms. Record this for R3. You can now insert the third resistor into the breadboard by again inserting the axial leads above and below the center canal. The next step would be to connect another black jumper lead from the second to the third resistor. Now add a third ammeter and connect the black clip lead to the top axial lead of the third resistor. Next, connect the red ammeter clip lead to the junction between the total current ammeter black lead and ammeter branch 1 and 2 red leads. Turn the DC power supply back on. Look at the ammeter for total current. It's reading 14.9 milliamps. Record this for IT. The ammeter for the first branch is reading 5.0 milliamps. Record this for IR1. The ammeter in the second branch is also reading 5.0 milliamps. Record this for IR2. Finally, look at the ammeter for the third branch. It's reading 4.9 milliamps. Record this for IR3. Notice that when you added the third resistor in parallel to the circuit, the total current increased from 10 milliamps to 14.9 milliamps. However, the total current is still equal to the sum of the individual branch currents. That is, 5 milliamps plus 5 milliamps plus 4.9 milliamps equals 14.9 milliamps.
Now, since the voltage across parallel branches is the same as total voltage, you can record 5.0 volts next to ER1, ER2, and ER3. Two observations can be drawn from this demonstration. 1. Adding parallel resistors to a circuit increases total current. And 2. Total current in a parallel circuit is equal to the sum of the individual branch currents. That is, IT equals IR1 plus IR2 plus IR3. This is known as Kirchhoff's current law. Returning to the circuit you just tested, you can verify your readings for current by using Ohm's law. Remember to use your memory aid. Since in this case you want to solve for current, cover the letter I, and you'll find that I is equal to E divided by R.
Let's start by verifying the current in branch 1. Since the voltage is 5.0 and the resistance is 1,000 ohms, you can verify current by dividing 5.0 by 1,000. The answer is 0.005 amps, or 5.0 milliamps, which matches your reading. The current in branch 2 can be verified by dividing branch 2 voltage, 5.0, by branch 2 resistance, 1,002 ohms. The answer is 4.99 milliamps, which is within tolerance, confirming the current in branch 2. Repeating this process, we can confirm the current in branch 3 by dividing branch 3 voltage, 5.0, by branch 3 resistance, 1004 ohms, which gives us 4.98 milliamps. This is again within tolerance, confirming the current in branch 3.
Using Ohm's law again, calculate the total resistance in the circuit. By covering R, you find that R is equal to E divided by I. The total voltage in this circuit is 5.0 volts divided by the total current, 14.9 milliamps. The total resistance, then, is 336 ohms when rounded. Notice that this is less than each of the individual branch resistances. That's because when resistors are connected in parallel, total resistance decreases. This value for the total resistance in the parallel circuit is known as the equivalent resistance. Remember, according to Ohm's law, resistance, R, is equal to voltage, E, divided by current, I. In parallel circuits, voltage is constant no matter how many parallel resistors are added. However, total current increases when resistors are added in parallel. Therefore, total resistance must decrease as resistors are added in parallel.
Returning to the schematic, let's change the resistance in both branches 2 and 3 so that each branch has a different resistance. This 1500 ohm resistor will be used in branch 2, and this 2000 ohm resistor will be used in branch 3. Keep in mind, in replacing resistors 2 and 3, all connections will be the same. On your notepad, again make columns for voltage, current, and resistance. Record 1000 ohms for R1. Using your ohm meter, check the 1500 ohm resistor. The meter reads 1.499 kiloohms or 1499 ohms. Record this for R2. Checking the 2000 ohm resistor, the meter reads 1.998 kiloohms or 1998 ohms. Record this for R3. Next, turn the DC power supply back on. On your notepad, record 5.0 volts for total voltage. You can also record 5.0 volts for ER1, ER2, and ER3. Remember, the resistors are connected in parallel, so the voltage is the same at each branch in the circuit. Look at the ammeter measuring total current. It's reading 10.8 milliamps. Record this for IT. Check the ammeter in branch 1. It's reading 5.0 milliamps. Record this for IR1. The ammeter in branch 2 is reading 3.3 milliamps. Record this for IR2. Finally, the ammeter in the third branch is reading 2.5 milliamps. Record this for IR3.
Again, notice that even though each branch has a different resistance, the total current is still equal to the sum of the individual branch currents. That is, 10.8 milliamps is equal to 5.0 milliamps plus 3.3 milliamps plus 2.5 milliamps. This again proves Kirchhoff's current law. You should also notice that branch 1, which has the lowest resistance, has the highest branch current, and branch 3, which has the highest resistance, has the lowest branch current. Again, you have verified Ohm's law. Remember, in parallel circuits, voltage is equal at each branch in the circuit. Therefore, as resistance increases, current decreases. Now that you know the total current and the total voltage, you can use Ohm's law again to determine the total resistance. By covering R, you find that R is equal to E divided by I. In this case, the total voltage, 5.0 volts, is divided by the total current, 10.8 milliamps, to give you the total resistance of 463 ohms when rounded. Record 463 for RT. Notice that the equivalent resistance of the circuit, 463 ohms, is always less than any of the individual branch resistances.
Just as there's a formula for total resistance in a series circuit, there's also a formula for total resistance in a parallel circuit. This formula is known as the reciprocal formula. It's derived from both Kirchhoff's current law and from Ohm's law. Here's how. Kirchhoff's current law states that total current in a parallel circuit is equal to the sum of the individual branch currents, that is, IT equals IR1 plus IR2 plus IR3. Ohm's law states that the total current IT is equal to total voltage, ET, divided by total resistance, RT. Therefore, by substituting the value for total current, according to Ohm's law, into Kirchhoff's current law, you get total voltage, or ET, divided by total resistance, RT, equals IR1 plus IR2 plus IR3. Ohm's law is also true for every part of a circuit. Therefore, the current in branch 1, or IR1, is equal to the voltage in branch 1, or ER1, divided by the resistance of branch 1, or R1. By substituting this value for branch current into Kirchhoff's current law, you get ET divided by RT equals ER1 divided by R1 plus IR2 plus IR3. The current in branch 2, or IR2, is equal to the voltage of branch 2, or ER2, divided by the resistance in branch 2, or R2. Substituting this value into Kirchhoff's current law, you have ET divided by RT equals ER1 divided by R1 plus ER2 divided by R2 plus IR3. The current in branch 3, or IR3, is equal to ER3 divided by R3. By substituting this for IR3, you now have ET divided by RT equals ER1 divided by R1 plus ER2 divided by R2 plus ER3 divided by R3.
As stated earlier, the voltage in a parallel circuit is the same at every point in the circuit. That is, ET equals ER1 equals ER2 equals ER3. By substituting ET for the voltage drops of each of the branches, you now have ET divided by RT equals ET divided by R1 plus ET divided by R2 plus ET divided by R3. Finally, because ET is constant throughout the equation, you can substitute a 1 for each ET. Now you have 1 divided by RT equals 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. This is the reciprocal formula. It's the standard equation used to determine the total resistance in a parallel circuit. Let's apply this formula to the circuit you tested earlier. Referring to your chart, R1 is 1,000 ohms, R2 is 1,499 ohms, and R3 is 1,998 ohms. Plugging the numbers into the formula, you get 1 divided by RT equals 1 divided by 1,000 ohms plus 1 divided by 1,499 ohms plus 1 divided by 1,998 ohms. 1 divided by 1,000 is 0.001. 1 divided by 1,499 is 0.0006671, and 1 divided by 1,998 is 0.0005005. Now add these numbers together to get 0.0021676. Then divide 1 by 0.0021676. This gives you 461 when rounded. Therefore, according to the reciprocal formula, total resistance, RT, equals 461 ohms, which is within tolerance.
As you've just seen, using the reciprocal formula is a convenient method for determining the total resistance in a parallel circuit. Some parallel circuits you'll test, however, will have only 2 branches. To determine the total resistance in a parallel circuit with only 2 branches, a different formula can be used. It's known as the product divided by the sum formula. The product divided by the sum formula is derived from the reciprocal formula. Here's how.
For parallel circuits with only 2 branches, the reciprocal formula reads 1 divided by RT equals 1 divided by R1 plus 1 divided by R2. First, find a common denominator by multiplying the right side of the equation by R1 times R2 divided by R1 times R2. Remember, R1 times R2 divided by R1 times R2 is equal to 1. By multiplying this by the right side of the equation, you haven't changed any values. You're just finding a common denominator. Now the equation reads 1 divided by RT equals R1 plus R2 divided by R1 times R2. By cross-multiplying, you get RT times R1 plus R2 equals R1 times R2. Finally, by dividing each side of the equation by R1 plus R2, you get RT equals R1 times R2 divided by R1 plus R2. This is the product divided by the sum formula. As stated earlier, it can be used to determine the total resistance in parallel circuits with only 2 branches. Let's apply the product divided by the sum formula to a circuit schematic.
This schematic represents a parallel circuit with only 2 branches. The first branch has a resistance of 1,000 ohms, and the second branch has a resistance of 1,500 ohms. Using the product divided by the sum formula, you get RT equals 1,000 ohms times 1,500 ohms divided by 1,000 ohms plus 1,500 ohms. RT then equals 1,500,000 ohms divided by 2,500 ohms for a total resistance of 600 ohms. Let's stop here and review what you've been shown.
Number 1. A parallel circuit is defined as a circuit with more than one path for current to flow, with a common voltage source for each path.
Number 2. Kirchhoff's current law states that total current in a parallel circuit is equal to the sum of the individual branch currents. In addition, total current increases as parallel resistors are added to the circuit. However, voltage is the same at every branch in the circuit.
Number 3. Total resistance in a parallel circuit decreases when parallel resistors are added, and is less than any of the individual branch resistances. The reciprocal formula is used to calculate the equivalent resistance for parallel circuits with more than 2 branches, while the product divided by the sum formula is used for parallel circuits with only 2 branches. In the next program, you'll be introduced to series parallel circuits. You'll see how to apply everything you've been shown to first simplify a series parallel circuit and then solve for all unknown values for that circuit.